Good evening everyone, my name is Rafie and today I'll be going through Euler's method and how we can derive it and properly use it. So in this example I used y equals to x squared as the graph, and I placed the tangent at x equals to 1. As you move away from x equals to 1, the distance from the slope to the tangent increases, but with Euler's method we have a tangent line but with course correction. So in here I have the same graph, however I differentiated y in terms of x to get 2x. Now I have the step size h equals to 1. So basically the initial position I give this graph is x equals to 1 and y equals to 1 via here. So now x equals for the formula of Euler's method, xn plus 1 equals to xn plus h, which is the step size. Similarly for y, we have yn plus h. However, as the value of x increases, the gradient slope of the graph, or the slope of the graph, gets even more steeper, and hence you have to multiply the step size by the function xn or yn, or the gradient of the slope. In this example, I have when n equals to 1, I have 1 plus 1 since h is the step size, and then for y I have 1 plus 1 multiplied by the previous gradient of the graph, which is 2. Hence I'll get y equals to 3 here. So Euler's method basically gives a better estimation of the slope tangent by giving the tangent course correction. Now let's look at the Excel. Let us now look at the Excel formula. In this cell I'll name it x, this cell y, and in this cell function xy, and I'll set my initial conditions via here. Y equals to 0, y is 1, and function xy using this differential equation, x over y squared, which is equal to 0. And then this cell I'll increase the x value by the step size, adding from the previous x value, which will be 0.1. Same thing for y, however instead of just adding by the step size, I'll multiply by the previous gradient and I'll get 1. Similarly here I'll use x over y squared for this side, which will be equal to 0.1, and I'll continue this all the way until I hit x equals to 1, so that I can find the approximate value of y when x equals to 1. So for here I'll get, rounding up to 5 decimal places, 1.339, and the gradient was 0.575. Now let's compare this to the actual calculated value. Let's now take a dive into how we can solve for the exact solution and compare it to Euler's method to find the error. We have dy over dx equals to x over y squared, and since it is separable, we can go through the normal procedure to get 1/3 y cubed equals to half x squared plus c. We can solve for c by using y equals to 1 and x equals to 0. We'll get c equals to 1/3. Now we can find y when x equals to 1, which will give us a value of 1.357 in 3dp. Now let us take a look at error analysis, which is basically the magnitude of y exact minus y Euler, which will have a value of 0.018. There's a minuscule error of 0.018 when comparing Euler's method to the exact solution using general solution, and hence this shows how accurate Euler's method is when computing more advanced differential equations, which is also one of its more important uses. Thank you for watching, and I hope this video was informative. Thank you and have a good day.